Just after the Big Bang, when stars and galaxies were only beginning to form, scientists envisioned a powerful instrument that could let us peer into the past and unlock the secrets of the universe's infancy. That vision led to the creation of the James Webb Space Telescope, an engineering marvel born from 25 years of dedicated research, innovation, and international collaboration. Designed to be the most advanced space observatory ever built, the Webb telescope is redefining our understanding of the cosmos. Unlike its predecessor, the Hubble Space Telescope, which focused primarily on ultraviolet and visible light, the James Webb Space Telescope specializes in infrared observations. This distinction is crucial. Because of the universe's constant expansion, light from the earliest stars and galaxies gets stretched into the infrared spectrum by the time it reaches us. By detecting this ancient infrared light, Webb allows scientists to look deeper into space and further back in time than any telescope before it. One of Webb's greatest strengths lies in its ability to see through cosmic dust. While visible light is easily blocked by interstellar dust clouds, infrared light passes through, offering unobstructed views of stellar nurseries, planetary systems, and galactic cores. This unique feature enables scientists to study regions of space that have remained invisible until now. The Webb telescope's journey began with a launch aboard the Ariane 5 rocket in December 2021. After a successful deployment, it traveled nearly 1.5 million kilometers from Earth to reach its destination, the second Lagrange point, or L2. This remote location allows the telescope to stay in a stable orbit, away from Earth's heat and light, ensuring the infrared sensors can function at cryogenic temperatures without interference. Once operational, the telescope quickly began delivering unprecedented data. Early observations revealed galaxies that formed far earlier than previously believed, some just 300 to 400 million years after the Big Bang. According to prevailing cosmological models, galaxies should have taken much longer to evolve, but Webb's data challenges that assumption. It found mature, well-formed galaxies that existed at a time when the universe was still very young. This discovery shocked astronomers. It suggests that galaxy formation may have begun almost immediately after the universe cooled enough to allow matter to clump together. If galaxies could form this quickly, then the processes governing their birth and growth must be far more efficient or fundamentally different than we imagined. But the surprises didn't stop there. When scientists analyzed the light from these ancient galaxies, they noticed something even more astonishing. Many of them contained heavy elements, metals such as carbon, oxygen, and iron. These elements are usually formed inside stars and released into space through supernova explosions. For such elements to be present, multiple generations of stars would have had to form and die in rapid succession. In other words, star formation in the early universe was not only fast, it was explosive. Some of the galaxies detected by Webb are unexpectedly massive. This challenges the standard timeline of cosmic evolution, which suggests it would take billions of years for such mass accumulation. Yet here were galaxies containing tens or hundreds of billions of stars, existing mere hundreds of millions of years after the universe's birth. This poses a profound question. Are our models of galaxy formation fundamentally flawed? Or is there a new kind of physics at play, one we haven't yet understood? Further complicating the puzzle, Webb detected some objects that didn't behave like normal galaxies or stars. Some emitted strange patterns of light, while others showed signs of energetic processes more akin to quasars or black hole activity. One possible explanation is that these could be primitive versions of active galactic nuclei, powered by supermassive black holes that somehow formed much earlier than expected. This raises yet another mystery. How did such massive black holes form so soon after the Big Bang? Our current understanding suggests that black holes grow slowly over time by consuming gas and merging with other black holes. But the Webb telescope is revealing black holes with masses equivalent to hundreds of millions of suns, existing in an era when the universe was still a toddler. These findings force scientists to consider more exotic scenarios, like the direct collapse of massive gas clouds or the existence of primordial black holes formed in the earliest moments of the universe. Another remarkable discovery was the presence of extremely compact and bright galaxies, some of which may have experienced bursts of star formation unlike anything we've seen locally. These intense star-forming regions could indicate environments so dense and energetic that they challenge known models of how gas cools and collapses to form stars. The images captured by Webb are not only rewriting scientific textbooks, but they're also offering a new kind of cosmic aesthetic, shimmering galaxies, structured in ways we've never observed, spread across the vast canvas of space. These aren't the diffuse, faint smudges we once assumed the early universe contained. Instead, Webb reveals vibrant, luminous galaxies, some with disks, bulges, and even spiral structures, all in place within the first billion years of cosmic history. The deeper we look, the more anomalies we find. One such anomaly is the discovery of what researchers call galaxy overdensities, regions where galaxies appear clustered together much earlier than models predict. These protoclusters may be the ancestors of today's massive galaxy clusters. Their early emergence suggests a rapid gravitational assembly process that cosmology struggles to explain. Then there's the strange issue of galaxy shapes and sizes. Some galaxies appear far too small and compact for their brightness. This hints at extremely dense star populations, possibly packed into regions just a few thousand light-years across. Others appear elongated or warped, suggesting violent gravitational interactions or mergers happening at a breakneck pace in the early universe. Even the basic assumptions about dark matter and dark energy, the invisible forces that govern cosmic expansion, are now being re-evaluated in light of Webb's observations. If galaxies formed earlier, more frequently, and more massively than expected, it could indicate that dark matter behaves differently in the early universe, or that dark energy's influence evolved over time. Webb is also opening doors to understanding exoplanets and the atmospheres of distant worlds. Though this is a separate branch of its mission, it complements the cosmic story. By analyzing starlight passing through alien atmospheres, Webb can detect chemical signatures, like water vapor, methane, or carbon dioxide, potential indicators of habitability. This connects the earliest galaxies to the ultimate question: could life have emerged elsewhere in the universe, even during those primordial epochs? As scientists continue to sift through the treasure trove of data from the Webb telescope, they are faced with a new reality, one where the universe's timeline is far more compressed, dynamic, and mysterious than previously thought. Every image, every spectral line, and every unexpected pattern of light forces us to reconsider the fundamental story of cosmic evolution. It's not just about finding distant galaxies. It's about understanding who we are, where we come from, and how the universe came to be as it is. The James Webb Space Telescope isn't merely a window to the past. It's a mirror reflecting the complexity of the universe, showing us how much we still have to learn. And perhaps, in its silent orbit far from Earth, it is whispering a profound truth to all of us: that the universe is more ancient, more active, and more astonishing than we ever dared to imagine. Stay curious. This is Discovery at 2.0.